Welcome back to the Deep Dive. This is where we break down complex technical topics, really getting into the essentials you need quickly and clearly. Today, we're diving deep. We're looking at the hidden layers, the invisible safety nets that protect every train journey, every passenger, everything moving on our railway networks. And just to grasp the stakes here, think about the scale. European railway accidents. They cost something like 4 billion euros every year.
It's huge.
Yeah, and tragically, in just 1 year, we've seen numbers like 841 fatalities, 569 serious injuries. These aren't just statistics. They really hammer home that safety.
Well, it's not optional.
Not at all. It's fundamental. It has to be systematic, a core discipline.
Exactly. So our mission today is to sort of demystify that systematic detective work, railway safety engineering. We're going to unpack the big three analytical tools, FMECA, HAZOP, FTA, UAP, and show you how they work together, how they become these invisible guardians for all of us.
And this deep dive is really aimed at you if you're maybe an engineering student just starting your career, or maybe you're just really passionate about railway safety. And we want to get beyond just the acronyms, Understand the functional safety lifecycle, because modern safety, it follows standards like EN 50126. It's structured.
Structured how?
Well, you move logically. Start high-level conceptual checks. Then you drill down, right down to the component level, checking failure modes during the detailed design. It's a process.
Okay, let's unpack that process then. Because you don't just jump into analyzing microchips, right? You start bigger picture.
That's right. You map the landscape first.
And the very first step, when the design might just be scribbles on paper.
That's the preliminary hazard analysis, PHA. It's foundational, absolutely essential, happens during that early conceptual design phase. Things are still emerging, maybe a bit fuzzy.
So you're not looking at specific bolts or wires yet?
No, not yet. It's broad brushstrokes. The main goal is just high-level hazard identification.
Okay, but how do you spot hazards if you don't even have the final design nailed down?
Good question. You lean heavily on history. Lessons learned, sometimes it's called. You look at similar systems, legacy stuff, what went wrong before, what hazards are already known in the industry standards. Accident reports. If you're designing new brakes, you ask, what are the common risks for any brake system? Wheel slip, maybe, brake fade, actuation failure, things like that.
Okay.
And the output. That's your first preliminary hazard analysis report. And that seeds the very first version of your main hazard log.
And I think it's really important for everyone listening to get this. PHA is required.
Yeah.
Even if the project seems low risk, low safety criticality.
Absolutely. Due diligence. Always. You have to capture those potential hazards right from the start.
Okay, so PHA sets the scene, then the design matures.
Yeah.
Gets detailed.
And that's when we transition to the system hazard analysis, SHA.
Right, so now we stop asking what could go wrong generally and start asking, okay, with our specific hardware, our software, the physical layout, how exactly could those general hazards actually happen here?
Precisely. SHA is the deep dive, the low-level assessment. It looks at how the hardware bits talk to the software bits, how humans interact with it, even environmental factors, dust, heat, vibration.
It's where the rubber meets the road, connecting the general PHA ideas to the specific system reality.
Exactly.
And this leads us to something crucial. You mentioned the SHA workshop requirement. It has to be a workshop, like people in a room or virtual, but together.
Non-negotiable. It has to be a workshop.
Yeah.
Because SHA is where the really critical engineering judgment happens, especially, and this is key, the SFARP assessment.
SFARP. Okay, let's break that down. SFARP.
So far as is reasonably practicable.
Right. The balancing act, safety versus, reality, cost, time.
Exactly. It's the balance. And you can't figure that out alone in an office. It needs that collective brain power.
So SFARP. It feels like the ethical and economic heart of this whole thing. How does a team actually decide, okay, this risk reduction measure, it's just not reasonably practicable anymore?
Well, it needs a proper documented trade-off analysis. Look, SFARP acknowledges you can't hit zero risk. It's impossible economically, often technically too. You reduce the risk down, until the point where adding more controls, well, the cost or the time delay or just the sheer technical difficulty would be massively out of proportion to the tiny bit of extra safety you might gain.
Can you give an example?
Sure. Maybe you have a triple redundant braking system going to quadruple redundancy. It might only shave off a tiny fraction of a % from the failure rate, but it could double the cost, the weight, the complexity.
Okay.
The workshop, with all the experts, technical, operations, finance people, they hash it out. They agree where that line is drawn. And crucially, they document why, so the decision is defensible later.
So the SHA workshop nails down the severity, the probability, checks the controls, and gets that SFARP justification. Where does all this vital info live? The evidence, the decisions, the verdict, as you put it.
It all lives in the Project Hazard Log, the PHL. This is the central hub. And it absolutely is a living document. It gets updated constantly, from PHA through design, testing, even operational changes years later.
That legal case file analogy you used, that really clicks. It's not just a list. It's got to stand up to scrutiny, potentially decades down the line.
It's the ultimate audit trail. Accountability. Every hazard gets a unique ID. Traceability is key. It lists the hazard that's the charge, the specific causes the evidence, the controls put in place the defense, maybe the required safety integrity level, SIL, that's the standard of proof, and then the sign-off, often with that SFARP justification, the final verdict.
Wow. So if something does go wrong years later...
Investigators, regulators, they go straight to the PHL. Was this risk identified? Was it managed? Was the decision justified? It's all there, or it should be.
We've talked about the main SHA. But modern trains are complex beasts, aren't they?
Yeah.
Sometimes you need to break the analysis down further.
Yeah, complexity often demands more granularity, so you might see variations, like SSHA, subsystem hazard analysis.
Okay, when would you use that?
Say you're building a train where the doors, the air conditioning, the lighting systems, they're all linked, interdependent. SSHA looks specifically at those subsystem interactions. Make sure a failure in one doesn't cascade unexpectedly into another.
Makes sense. And interfaces. Trains don't exist in a vacuum.
Exactly. That brings us to IHA interface hazard analysis. This is super critical because, yeah, systems connect to other things, maybe new rolling stock connecting to old signaling, or the train interacting with platform screen doors.
Those connection points sound like potential weak spots.
They often are. The interface boundary is frequently where the highest risks lie. IHA focuses right there.
Okay, SSHA for internal complexity, IHA for external connections. What about the human side, the procedures?
That's where OSHA comes in, operating and support hazard analysis. This usually happens later in the design phase. It checks. Can this thing actually be operated safely? Maintained safely, supported safely throughout its life? OSHA identifies the needs for administrative controls.
Like
Training manuals, clear operating procedures, proper maintenance schedules, things that ensure a technically safe system stays safe in human hands. It catches risks like, say, performing maintenance steps in the wrong order or forgetting refresher training.
Right. We've got the framework mapped out, PHA setting the stage, SHA getting into the weeds.
Yeah.
Now let's zoom in on the actual tools engineers use within that framework. First up, FMECA, the component detective.
Ah, yes, FMECA. Failure mode, effects, and criticality analysis. It's a cornerstone of reliability engineering, and it's an inductive bottom-up method.
Inductive
Meaning, we start with something known, like a specific component failure, and we reason forward to figure out the unknown consequences. We ask, okay, if this specific relay fails open, what's the immediate effect? What's the effect on the subsystem? And ultimately, what's the effect on the whole train's operation?
It sounds incredibly detailed, almost painstaking.
It is, but that rigor is its strength. It forces you to list every key component and then brainstorm every plausible way it could fail.
So what are the steps?
Okay, first, you break the system down into manageable chunks, functional blocks. Then, for each component in a block, you identify all its potential failure modes. For example, a pump. It could fail stuck on or stuck off. It could leak. Maybe it works, but only sometimes, intermittently.
Oh, got it. Failure modes. Then
you trace the effects. What's the local effect? What happens at the subsystem level? And what's the big picture, system-wide effect? Does a sensor failing off just trigger a warning light? Or does it actually delay the brakes engaging? Big difference.
Okay, modes, effects, and the C in FMECA. Criticality.
Right. The criticality assessment, this is what tells you where to focus your effort, your budget. And that relies on calculating the RPN.
The risk priority number.
Exactly. RPN is calculated by multiplying 3 factors. Severity, S times occurrence, O times detection, D.
Okay, let's break those down. Severity.
Severity is usually scored maybe 1 to 10. 1 might be no real effect, while 10 is catastrophic failure.
Yeah.
Potential fatalities, major system damage. Occurrence is similar, 1 to 10, based on how often you estimate that particular failure mode might happen. Is it extremely rare or fairly common?
Okay, severity, occurrence, now detection. This is the one that trips people up sometimes, right?
Yeah.
Because a high score is bad.
That's the one. It's counterintuitive. A high detection score, maybe a 9 or 10, means the failure is essentially undetectable by the current design. It could happen, and you wouldn't know until it's too late.
And that drives the RPN way up.
Way up. A high detection score screams redesign needed or add monitoring. Conversely, a low score, like 1 or 2, means the failure is obvious. Maybe an alarm sounds, or the operator sees it immediately, or built-in diagnostics flag it.
So FMECA, by calculating that RPN, gives you hard numbers to justify spending money on safety improvements.
Precisely. It provides quantitative evidence.
Let's use that HVAC case study you mentioned. 132 components, 163 failure modes found.
Right. And the really striking thing, the key finding, was that 123 of those failure modes, the vast majority, were flagged as highly undetectable. High D score.
Wow. Like what kind of failure?
Well, think about maybe a tiny hidden crack developing in a coolant pipe. It's not a sudden burst. It leads to a slow leak, a gradual loss of cooling efficiency. It might not cause immediate disaster, but over time, internal temperatures creep up. Maybe sensitive electronics start getting flaky or passenger comfort degrades. But a simple on-off temperature sensor might not catch it until it's quite advanced.
So if FMECA flags 123 undetectable modes like that, what do? Redesign everything.
Not necessarily redesign, but enhance the monitoring. They couldn't just rely on simple, is it working or it's not working diagnostics. They had to move towards indirect condition monitoring. Instead of just a basic temperature sensor, maybe they added vibration sensors to the pumps. Or they started monitoring tiny changes in the electrical current draw over time, using clever algorithms to spot patterns that hint at degradation before a full failure.
And those extra, more complex sensors were justified because?
Because the FMECA provided the RPN data. It showed quantitatively that the risk from those undetectable modes was unacceptable under SFA's FAP. It proved the investment was necessary.
Okay, FMECA, bottom up, component focused. Now, tool number 2, HAZOP, hazard and operability studies. This feels different.
More.
Exploratory.
Completely different mindset. HAZOP is exploratory, yes. It's brilliant for situations where you suspect there might be unknown causes leading to unknown consequences. You don't necessarily know what could go wrong or how.
When would you typically use it?
Often on systems involving flows like fluids or data or energy, or complex processes, complex control logic, where interactions are key.
And you said its brilliance lies in the structure it imposes on, well, brainstorming.
Exactly. It stops it from being just a random chat. It uses guide words. That's the core mechanism.
Right, the guide words. Tell us how they work. How do they force the team to think outside the box?
Okay, the team first breaks the system down into logical nodes. Think of a node as a point where something is transferred or controlled, a pipe junction, a data bus, a control valve. Then, at each node, for each design parameter like flow, pressure, temperature, data value, they apply a set of standard guide words to challenge the design intent.
What are some key guide words?
Things like no or not, more, less, as well as part of reverse, other than.
Wait, let's take an example. Say a node is passing a control signal to points equipment on the track. How would you apply, say, no?
Applying no to the signal parameter forces the team to consider. What happens if there's no signal when there should be, or the signal is not correct?
And more or less.
More could mean the signal is sent too frequently or its value is too high. A less could mean it's too infrequent or the value is too low. As well as is interesting.
How so?
It makes you think about unintended combinations. What if the intended automatic signal goes out as well as an unexpected manual command, or as well as some spurious noise on the line?
And reverse on a signal.
Reverse could mean the signal logic is flipped. Instead of lock points, it sends unlock points. Or for flow, it literally means flow in the opposite direction to the design intent. Maybe due to wrong installation or a back pressure event, it forces you to question basic assumptions.
It sounds like a really rigorous mental workout. But you stress that the success of a HAZOP really depends on how the workshop itself is run.
Oh, absolutely critical. Cannot be overstated. 2 things are vital before you even start. First, the documentation, the P&IDs, the logic diagrams, whatever describes the design intent at that node must be accurate, complete, and frozen, usually at least 2 weeks before.
Frozen? Why frozen?
Because trying to ASOP a design that's still changing is like trying to hit a moving target. It's chaos, completely useless. Second, the team size. Keep it manageable.
How many people?
Ideally, 10 to 15 max. You need the key subject matter experts design, operations, maintenance, maybe safety, but any bigger, and people clam up. The dynamic exchange you need for creative hazard spotting just dies.
And the facilitator's role sounds crucial too, like a strict conductor.
Pure discipline is right. The facilitator has one main job during the guide word application. Keep the team focused, laser sharp on identification only.
Not on solving the problems.
Absolutely not. The human brain immediately wants to jump to solutions. Oh, if that happens, we could just add a sensor here. The facilitator has to constantly pull them back. Identify the deviation, the cause, the consequence, any existing safeguards. Document it. Move to the next guide word. Solutions come later, outside the HAZOP meeting.
Got it. Stick to identification.
And one more thing, with so much digital control now, we often run HAZOPs, computer HAZOPs. Same principle, but the guide words are adapted to focus specifically on data flows, timing, sequence errors, data corruption, software logic issues.
Okay, FMECA bottom-up HAZOP explores the unknown. That leaves FTA, fault tree analysis. This one works backwards.
Exactly. If FMECA is cause leads to effect, FTA is the opposite. It's the master of working backward from the disaster scenario. It's a deductive top-down method.
Deductive how?
You start with the undesired top event. This is the big one. You absolutely want to prevent a train collision, a major derailment, a catastrophic fire on board.
Okay, you define the nightmare scenario first.
Right. Then you ask, okay, we know this could happen. What are all the possible combinations of lower-level failures, component failures, software bugs, human errors that could logically lead to this top event?
And it uses a specific visual language, right? Boolean logic gates.
Yes, the fault tree is built using simple logic gates, mainly A&D gates and OR gates, to link failures together.
Explain the difference. Why are they important?
Okay, think of an OR gate. If you have several potential failures feeding into an OR gate, any one of those failures happening is enough to trigger the event above the gate.
So an OR gate highlights a weakness, a single point of failure.
Potentially, yes. It shows paths where there isn't redundancy. Now contrast that with an A&D gate. For the event above an A&D gate to occur, all of the input events below it must happen simultaneously, or at least in the necessary sequence.
So A and D gates represent redundancy, robustness.
Exactly. Engineers strive to design systems so that critical failure paths have to go through A&D gates. It means multiple independent things have to fail together, which is much less likely.
And you can put probabilities on these base failures and calculate the likelihood of the top event.
Yes, if you have good failure rate data for the basic events at the bottom of the tree, like component failure rates from FMECA or human error probabilities, you can propagate those probabilities up through the logic gates to estimate the probability of the top event.
And this helps identify the weakest links.
Precisely. It leads you to the minimal cut sets.
Minimal cut sets.
A minimal cut set is the smallest group of basic failures that, if they all happen, will guarantee the top event occurs. FTA software identifies these cut sets. If your analysis reveals a cut set with only one basic event, a single failure, that leads directly to a catastrophic top event, well, that's a major red flag. That component or function must be redesigned, probably to introduce redundancy, effectively putting that path behind an A&D gate.
So it visually proves where the critical vulnerabilities are.
And demonstrates how the implemented safety measures address them. It's essential for building the safety case.
That adjacent track accident analysis you mentioned, the ATA, how did FTA help there?
Right. The ATA is a good example of modeling a complex sequence. The top event was collision with a derailed train on an adjacent track. The FTA broke that down. It visually confirmed that for this specific top event to happen, you need three distinct things to occur, essentially simultaneously. 1, the initial derailment of the first train. 2, the physical intrusion of that derailed train onto the adjacent track area. And 3, crucially, the presence of another train on that adjacent track at that precise time and location.
So it's three things needing to align, like an A&D gate situation.
Exactly. By modeling these three prerequisites probabilistically behind an A&D gate, the FTA helps engineers understand the relative contribution of each factor. They can then focus resources on reducing the probability of the most likely combinations of failures, not just isolated events.
Before we move on from tools, you mentioned a couple of others, complementary ones.
Yeah, just briefly. Reliability block diagrams, RBDs, are often used alongside FMECA. They're visual maps showing how components are functionally connected in series, meaning if one fails, the system fails, or in parallel, meaning there's redundancy. They're great for calculating overall system reliability based on component data.
Okay, RBDs for reliability calculation. And the other?
Bow tie analysis. This one's becoming more popular. It's a nice visual that combines FTA and another technique called event tree analysis. You put the main hazardous event, the thing you're worried about, in the center knot of the bow tie. On the left side, you basically have a fault tree showing all the causes, threats, and the barriers you put in place to prevent the event, like safety controls.
So the left side is prevention.
Right. And the right side maps out what happens if the event occurs anyway, the different potential consequences, and the barriers you have in place to mitigate those consequences, like emergency response, containment systems.
So prevention on the left, mitigation on the right.
Exactly. It gives a really neat single-picture overview of the whole risk management strategy, both proactive and reactive barriers.
Okay, we have the tools FMECA, HAZOP, FTA, that tell us how to find the potential failures. But how safe is safe enough? That's where standards come in, isn't it?
Absolutely. The standards define the required level of safety performance, while the big, overarching functional safety standard is IEC 61508.
Or the foundational one.
The railway world really operates under a specific set of European standards, the CNWLIC standards, primarily EN 50126, EN 50128, and EN 50129. For engineers listening, knowing the difference is crucial.
Okay, let's differentiate them. EN 50126.
50126 is the big umbrella. It defines the whole RAM's lifecycle reliability, availability, maintainability, and safety. It lays out the required process for managing safety throughout the entire project lifecycle, from the initial concept right through to decommissioning the system years later.
So 5126 is the how-to manual for the overall safety management process. What about 50128?
EN 50128 drills down specifically into software. Think about how much software runs modern railway signaling, train control, diagnostics, everything. 50128 dictates the stringent requirements for developing, validating, and verifying safety-critical software. Coding standards, testing methods, documentation, it's all in there.
Okay, process is 50126, software is 50128, that leaves 50129.
EN 50129 covers the hardware and the overall system acceptance for safety-related electronic systems. It specifies what evidence is needed to prove the hardware is safe and that the integrated system meets its safety requirements. It outlines the final checks and documentation needed before you can actually put the system into service.
So to get a safety case approved, you really need to satisfy all three. The process, 50126, the software, 50128, and the final system evidence, 50129.
That's generally the framework, yes. They work together.
And woven through all these standards is this concept of the safety and integrity level, SIL. You called it the system's security clearance earlier.
It's a good analogy. SIL is the quantifiable target for how reliable a specific safety function needs to be. It's a measure of risk reduction. SIL1 is the lowest level, maybe for a simple monitoring function. SIL4 is the highest, reserved for functions where failure could have catastrophic consequences.
Let's talk about SIL4. What does that actually mean in terms of how unlikely failure has to be? The numbers are pretty mind-bending, aren't they?
They really are. A SESI-BOR safety function, like the Automatic Train Protection ATP system.
That's the system that automatically brakes the train if the driver misses a red signal or goes too fast.
Exactly that. The ultimate safety net. For a SIL4 function like ATP, the standard demands a probability of dangerous failure on demand PFD, somewhere between 10⁴ and 10⁵.
10 to the -4 to 10 to the -5. What does that mean in real-world terms?
Okay, think about it this way. Achieving SIVOL certification implies that the probability of that safety function failing dangerously when it's needed is calculated to be roughly equivalent to one dangerous failure in 10,000 years of continuous operation.
1 in 10,000 years. That seems almost theoretically impossible for any single piece of equipment. How on earth do engineers demonstrate that level of reliability?
You're right. You can't achieve it with just one simple component. It absolutely requires massive redundancy and diversity, proven through rigorous analysis like FTA and RBDs.
So multiple backups.
Multiple independent backups. We often use techniques like triple modular redundancy, TMR. You might have 3 completely separate computers or processing channels, all performing the exact same safety calculation using potentially diverse hardware or software.
3 doing the same job. Why 3?
It enables 2 out of 3 voting logic. If one channel produces a different result, maybe it failed, the other 2 correct channels can outvote it and ensure the save action is still taken, or the system fails into a safe state.
So one failure doesn't bring the system down.
Right. The fault tree analysis for a TMR system has to show that a dangerous failure of the overall function requires the simultaneous independent failure of at least 2, often all 3, channels. That combination of failures is what pushes the overall probability down into that incredibly low SIL4 range. $10 roll.
That explains why achieving SL4 is so complex and expensive. And why not everything needs to be SL4. ATP, yes, but other systems.
Correct. Systems like automatic train operation, ATO, which handles the smooth driving, stopping at stations precisely, or automatic train supervision, ATS, the central control room functions are typically assigned a lower SIL, often SIL2.
Why lower for ATOTs?
Because their failure, while inconvenient or disruptive, doesn't usually have the same immediate catastrophic potential as an ATP failure. The SIL4 ATP layer is still there underneath, acting as the ultimate backstop. The SIL assignment is always driven by a thorough hazard analysis of the potential consequences of failure.
Okay, we started this whole dive talking about accident statistics. Let's bring it back to that. How successful has this rigorous, standards-based approach actually been?
It's easy to focus on the major accidents that make headlines like Washington Metro in 2009 traced back to a track circuit failure, or Ladbroke Grove in the UK, a terrible human error collision. These events are tragic and rightly drive safety improvements. But we have to acknowledge the bigger picture. Systematic railway safety engineering overall has been incredibly successful at preventing these operational accidents.
And the data, particularly looking at the U.S., paints an interesting picture about where the real risks lie today.
It really does. It's a statistic that often surprises people. In the U.S., something like 95% of all rail-related fatalities don't happen to passengers or crew on the train during operations.
95%. Where do they happen then?
They happen primarily at level crossings, cars, or pedestrians trying to beat the train and from trespassing on the tracks. The number of people killed while trespassing on railway property in the U.S. far, far outweighs the number killed in actual train operating accidents.
That's quite something. It speaks volumes about the effectiveness of the operational safety systems, the SIL4 systems we've been discussing.
It does. And you see the progress in other metrics, too. The U.S. rail industry, for instance, saw about a 40% reduction in derailment rates and an incredible 80% reduction in hazardous materials accidents between roughly 2005 and 2024.
And that improvement isn't luck.
Not at all. It's a direct result of systematically applying these safety lifecycle processes, like those in EN 5012C6, and using tools like FMECA and FTA to rigorously identify and mitigate risks, eliminating those single points of failure and hidden hazards.
Okay, let's shift from the standards and general principles to some really cutting-edge applications. The Middle East has some massive rail projects that are really pushing the boundaries of safety assurance, especially with driverless tech.
Absolutely. Those projects are fantastic real-world case studies. Take the Dubai Metro. It's been running as the world's longest driverless network since 2009. Its safety case had to tackle unique challenges from the environment.
Right. This is where the detailed FMECA thinking comes back in considering factors beyond just pure mechanics or electronics, like the desert environment.
Precisely. Extreme heat, pervasive fine dust, and sand. These things introduce failure modes you just don't encounter in, say, Europe. For example, standard smoke detectors in the stations. They'd be triggering false alarms constantly because of the heat and dust.
Which could lead to people ignoring real alarms or disabling the system.
Exactly. So Dubai Metro had to source and validate specialized fire detection systems. They used Hochiki sensors, for instance, which were specifically engineered and tested to work reliably maintain high integrity, but have very low false alarm rates, even with high dust levels and ambient temperatures. You have to ensure your safety system is robust against nuisance trips in the specific operating context.
And safety isn't just about the trains running on the main line, is it? The depots, the maintenance areas?
Huge risk areas, especially with automated trains moving around without drivers. Dubai uses sophisticated depot personnel protection systems, DPPS, like the one from Zone Green.
How does that work?
It uses things like physical derailers, locked points, and complex electronic interlocking, all tied to worker logon systems. When a maintenance crew needs to work on a specific section of track in the depot, they log in, and the DPPS physically prevents any train from being routed into that zone and ensures the traction power is isolated. It's about physical and administrative controls protecting human life where people interact closely with automated systems.
Now, the scale of the Riyadh Metro project, that must present its own unique safety assurance challenges.
Immense. Riyadh is said to be the biggest driverless system globally, 176 kilometers. For a project of that sheer size and complexity, involving multiple international contractors and consortia, while ensuring consistent safety practices across the board is vital.
So how do they manage that?
The client mandated the appointment of an independent safety assessor, or ISA. Often, this is a specialized third-party consultancy.
ISA, what's their role? Are they designing the safety systems?
No, they don't design anything. Their job is independent oversight. auditing. They review the main contractor's safety plans. They audit the hazard analysis activities, the PHAs, SHAs, HAZOPs. They scrutinize the evidence backing up the SIL claims for critical functions. They check the completeness and rigor of the project hazard log.
Across the whole project.
Across the entire project lifecycle. They act as the independent check, verifying that the developers have correctly followed the required Senelec standards and that the documented safety evidence is robust, complete, and convincing. Their final stamp of approval is usually essential before the system can be certified for passenger service.
Okay, shifting focus slightly. The rise of these driverless systems brings up what you called the driverless paradox.
Yes, it's a fascinating social and technical issue. The paradox is this. Pretty much all the data shows that automated driverless trains are statistically safer than trains driven by humans.
Safer. Why?
Because automation eliminates the single biggest cause of railway accidents worldwide. Human error, fatigue, distraction, misjudgments, signal passed at danger. Automation doesn't suffer from these.
What?
But public perception and even some professional concern remains wary. People worry about the possibility of a catastrophic system-wide failure of the automation itself, or they worry about the lack of immediate human intervention capability in an unusual emergency. So you have this tension. The data shows lower risk, but the perceived risk or the fear of certain types of failure remains high.
Managing perception versus statistical reality. A classic engineering communication challenge.
Definitely.
Now, beyond the trains themselves, technology like AI and the Internet of Things, IoT, is starting to change the safety analysis process too, isn't it?
Hugely. We're seeing a major shift towards predictive maintenance. Instead of just fixing things when they break or on a fixed schedule.
You've got to predict failures before they happen.
Exactly. You embed sensors everywhere, measuring vibration on axles, acoustic signatures from bearings, thermal profiles of equipment. All this data streams back constantly.
And AI comes in.
AI algorithms analyze this flood of data, looking for subtle patterns, anomalies, deviations from normal signatures that indicate a component is starting to degrade long before it actually fails catastrophically.
So you can intervene proactively.
Precisely. You can schedule maintenance targeted at that specific component, reducing the chance of unexpected high-risk failures like broken rails or bearing seizures that can cause derailments. It essentially turns FMECA from a static design analysis into a dynamic, real-time operational tool.
That sounds incredibly powerful for improving safety.
Yeah.
But certifying those AI systems, especially for high-integrity applications, that must be a massive hurdle for the standards bodies.
It's the defining challenge right now. Traditional safety systems, the ones we certify to SIL3 or ASI4, are generally deterministic. You can trace the logic. If condition X occurs, then safety action Y must happen. We can analyze and verify that logic path.
But AI isn't always like that.
Modern machine learning, especially deep neural networks, can sometimes act like black boxes. The AI might predict a potential track defect with, say, 99.8% confidence based on sensor data, but it might be incredibly difficult for it to explain why it reached that conclusion in a way that satisfies traditional safety verification methods.
The explainability issue.
Exactly. How do you provide assurance to a SIL4 level for a system whose decision-making process isn't fully transparent or mathematically traceable in the conventional sense? Developing new regulatory frameworks, new validation techniques that can accommodate these probabilistic learning systems while still ensuring ultra-high integrity. That's a huge area of work right now.
Okay, for everyone listening who's maybe studying engineering or just starting out and thinking this railway safety field sounds interesting, let's get practical. What are the essential skills, the competencies needed to actually do this work successfully, both hard and soft skills?
Right. On the hard skills side, you absolutely need mastery of these core risk assessment methods we've discussed, FMECA, HAZOP, FTA. You need to be comfortable with the concepts, the calculations, understanding failure rates, probability, how to use the tools. And underpinning all that, you need a deep functional understanding of the standards, especially the Senelec trio, 50126, 50128, 50129. Knowing which standard applies when, what evidence it requires, that's fundamental. Reliability engineering principles, too.
But it's not just about the technical chops, is it? You mentioned soft skills being critical, especially for things like SFARP judgments and running those workshops.
Hugely critical. Perhaps the most underrated practical skill is workshop facilitation. Leading a HAZOP or an SHA session effectively is tough. You've got diverse experts in the room, electrical, mechanical, software, operations, maintenance folks. You need to draw out their knowledge, manage disagreements, keep everyone focused, ensure all voices are heard, but prevent it descending into chaos or endless solution debates.
That sounds challenging.
It is. And alongside that, strong stakeholder management is key. You're dealing with project managers, clients, regulators, and crucially, technical communication. You have to be able to take complex technical risks, like explaining what an RPN of 400 really means, or why a $10 5-bar probability requires triple redundancy, and translate that into clear, concise business language that senior managers or non-technical executives can grasp, especially when they need to sign off on a difficult SFIP decision.
Okay, let's talk about avoiding mistakes. What are the common pitfalls that you see tripping up engineers, especially early career ones, when they're working on safety processes?
Good one. Pitfall number 1, using generic off-the-shelf failure rates. You see engineers pulling component failure data straight from standard handbooks.
What's wrong with that?
Because those handbook values are usually based on ideal conditions. Railway equipment operates in brutal environments. Constant vibration, huge temperature swings, dust, moisture. If you don't use failure rate data that's specific to the actual application, or at least adjusted for the real operating stresses, your FMECA and FTA calculations could be wildly optimistic. You'll underestimate the true risk. The whole safety case could be built on shaky foundations.
So context-specific data is key. What's another common mistake?
Neglecting human factors and the operational reality. Sometimes the analysis focuses too much on the hardware and software failures. But systems are operated and maintained by people. You must incorporate the probability of human error into the analysis in maintenance procedures, in operator actions, in emergency response. A perfectly designed SIL4 system can potentially be rendered unsafe by flawed procedures or inadequate training. Human failures need to be basic events in your fault trees where relevant.
Right. Don't forget the people. And the third pitfall, you hinted at it earlier.
Poor workshop execution. This kills the effectiveness of SHA and HAZOP. It can happen in several ways. Inadequate preparation, like trying to run the workshop before the design is properly frozen or the documentation isn't ready, or letting the team get too big so no real discussion happens. And the big one, letting the workshop degenerate into solution brainstorming instead of sticking rigidly to hazard identification. If people jump to fixes too early, they stop looking for other hazards. You get prematurely satisfied with easy answers and potentially miss significant risks.
Okay, valuable warnings there. So for someone listening who's maybe 0 to 2 years into their career, keen to build expertise in this area, what should they actively try to do?
Get involved, but start by listening and learning the process. Offer to be the scribe, the note taker, in hazard workshops like SHA or HAZOP. Just being in the room, seeing how experienced engineers identify hazards, how they use guide words, how they debate SFARP, it's invaluable. Focus on really understanding the project hazard log. Learn how to read it, how to update it correctly, how to trace a hazard from its initial identification in PHA right through to its final closure and verification. Master the database and the language.
Good starting point. And for someone maybe a bit further along, 2 to 5 years experience, ready to get more hands-on.
Now's the time to start applying the tools under supervision. Ask to conduct an FMECA on a smaller, less critical subsystem. This builds practical skill with the methodology, with calculating RPNs. Try co-facilitating a PHA workshop with a senior engineer, and start getting involved in the SAL determination process. Help gather the evidence, do the initial analysis for assigning SILs to new functions or modifications, supporting the senior engineers who will make the final call. Build that standards knowledge practically.
It sounds like a clear progression path, from observing and documenting to applying tools on subsystems, eventually leading complex analyses like FTA, developing full safety cases, and maybe even becoming one of those independent safety assessors on huge projects like Riyadh.
Exactly. It's a field where experience and methodical practice really build deep expertise. #tag outro. So just to wrap up our deep dive today, remember, railway safety isn't ad hoc. It's a systematic life cycle driven by standards. You start broad with preliminary hazard analysis, identifying the potential risks early on. Then system hazard analysis drills into the specific design details, forcing that critical SFARP assessment. And within that framework, we have our key analytical tools: FMECA, the bottom-up detective, looking forward from component failure modes; HAZOP, the structured brainstorm, exploring the unknown deviations deviations from design intent using guide words, and FTA, the top-down investigator, working backward from major accidents using logic gates to find vulnerabilities and verify redundancy, all benchmarked against demanding safety integrity levels.
We've definitely seen how this rigorous systematic approach has led to massive safety gains worldwide. It really works. But maybe let's leave our listeners with a final thought to chew on, especially thinking about AI in the future. We're increasingly using algorithms for parts of this analysis. AI can crunch sensor data, maybe spot patterns humans miss, ensure a kind of mathematical completeness in checking failure combinations. But does AI, as it stands today, truly possess the deep tacit engineering judgment, the contextual understanding, the, dare I say, ethical reasoning needed to make those nuanced SFARP calls?
That's the million-dollar question, isn't it? Can an algorithm truly determine what is reasonably practicable when you're fundamentally balancing the potential cost of human life against the cost and feasibility of implementing ever more complex safety measures? That's probably the central safety philosophy challenge we face as automation advances.
Indeed. Safety, as we've heard, is definitely no accident. It's the hard-won result of systematic, meticulous analysis by dedicated professionals using these powerful tools and frameworks. So embrace the methodologies, really internalize those standards, and always strive for the highest levels of safety integrity in whatever you design or operate. Thank you for joining us for the deep dive.
Thanks for listening to Safe Tracks, the System Safety Assurance podcast. Here, we talk all about how safety assurance keeps our railways running safely, smoothly, and reliably every single day. If you're curious about RAM management, RAM analysis, and how reliability is actually calculated, check out the RAMs Ready podcast playlist on this channel. It's packed with great insights. And hey, don't forget to subscribe and tap the notification bell so you'll know the moment a new episode is out. Until next time, stay safe, stay assured.